Hello, my dear students. I will continue from yesterday class. We'll discuss today what is neutral axis. Axis along the length of the beam which remains unstressed when it is bent. It is the region that separates the tensile forces from compressive force. That is, bending stress equal to 0. The position of the neutral axis must pass through the centroid of the section. Hence, this position is important. You can see here, this is the position of the neutral axis. This is neutral axis, and this because of this it gets compressed, so the fibers become shorter, and so there will be a compression stress, and here the fibers becomes longer, so there will be a tensile stresses are developed. So this is the position of the neutral axis. We'll see what is moment of resistance. On one side of the neutral axis there are compressive stresses, and on the other there are tensile stresses. These stresses form a couple whose moment must be equal to the external moment M. The moment of this couple which resists the external bending moment is known as moment of resistance. When a beam is loaded, it is bent and subjected to bending moments. Consequently, longitudinal or bending stresses are induced in cross section. In order to determine the practical utility of any beam, it is very necessary to establish a relationship between the radius of curvature to which the beam bends, the bending moment, the bending stress, and its cross-sectional dimensions. The equation which connects these quantities is known as the bending equation. So this bending equation is given by this m divided by I is equal to sigma divided by y is equal to E divided by R. Okay, so this equation is called as bending equation. Also, it is called as Bernoulli-Euler bending equation, where E is equal to Young's modulus, R is radius of curvature, M is bending moment at the section, and I is moment of inertia about the neutral axis, and this is that is bending stress, and y is equal to distance of the fiber from the neutral axis. Okay, and so this equation is very important. You always remember to solve any type of the problems. Okay, and here we'll see what is section modulus. We know this relationship, m divided by I is equal to sigma divided by y. Okay, is equal to E divided by R. We'll consider only these four terms. M divided by I is equal to sigma divided by y, or how you can write sigma B or bending stress. You can write either sigma or sigma B, no problem. So that is equal to M into y divided by I. It shows maximum bending stress occurs at the greatest distance from the neutral axis. Always maximum bending stress occurs at the greater distance, means at the extreme fiber. Let y maximum is equal to distance of the extreme fiber from the neutral axis. Okay, sigma b, that is maximum bending stress at a distance y maximum. So sigma b maximum is how you can write m into y maximum divided by I, where m is the maximum moment carrying capacity of the section. So if you write in terms of m, what this equation becomes sigma b into I divided by y maximum. So this I divided by y maximum, that is called as section modulus and is represented by the symbol z. So how you can write sigma b into z. Z is nothing but I divided by y maximum, that is equal to the ratio of moment of inertia to the distance of the extreme fiber from the neutral axis. It mainly gives the property, it indicates the property of the section. The unit is millimeter cube or meter cube, because see, I is millimeter power 4 divided by y is mm, so it becomes millimeter cube or meter cube. There are different section modulus expressions of various standard cross sections. Let us see for the rectangular section first. This is a rectangular section, width b and depth d. This is the position of the neutral axis cg, the position of cg. So this distance, that is CG located exactly at the center. So Y maximum is equal to D divided by 2, means distance from the neutral axis to the extreme fiber. Okay, now all of us, we know that moment of inertia for rectangular section is BD cube divided by 12. So Y is equal to now d divided by 2. So z is equal to moment of inertia to a ratio of moment of inertia to the y maximum. So moment of inertia is bd cube divided by 12 divided by y maximum, that is equal to d divided by 2. So when you simplify this, that becomes z is equal to 1 divided by 6 into bd square. Simplify this. This 2 goes here and d comes here. So 2 ones are and 6. So d get cancelled. So 1 divided by 6 bd square. So let us see for hollow rectangular section. Now consider the section of the size B and D with the symmetrical openings BXD as shown in the figure. Okay, so this is capital D or outer section, outer distance. Okay. The depth, and this is B is overall breadth, and inside that is small b and this is small d. So I is equal to BD cube divided by 12 minus small BD cube divided by 12. Simplify this, you can write in terms like this also, 1 divided by 12 into BD cube minus BD cube. So Y is equal to here capital D by 2. Okay, Y maximum is capital D by 2. So when you substitute Z is equal to I divided by Y maximum, you get 1 divided by 6 into capital BD cube minus small BD cube divided by T. Okay, this is for hollow rectangular section. Now we'll see for circular section. Circular section, this is a circle of radius R and diameter D. So Y maximum is equal to D divided by 2, diameter divided by 2. For circular section, I is equal to pi d raised to 4 divided by 64, and Y maximum is D divided by 2. When you substitute in the equation, section modulus or Z is equal to I divided by Y maximum. I is equal to pi d raised to 4 divided by 64 into divided by d by 2. You get pi d cube divided by 32. Okay, next for hollow circular section, this is outer diameter capital D and small d is inner diameter. So Y maximum is capital D divided by 2. So I is equal to, for a hollow circular section, pi divided by 64 d raised to 4 minus pi divided by 64 into small d raised to 4. So when you write, you can write like this also. So extreme fiber distance, that is Y maximum is equal to D divided by 2. So Z is equal to I divided by Y maximum, that is equal to pi divided by 32 D into D raised to 4 minus small d raised to 4. This is the section modulus for hollow circular section. So these four are important. You should know always. Okay, let us solve some example on this. A rectangular beam 60 mm wide and 150 mm deep is simply supported over a span of 6 meter. If the beam is subjected to central point load of 12 kN, find the maximum bending stress induced in the beam section. This is the given problem. Okay, B is given, that is 60 mm and D is 150 mm and span is equal to 6 meter. If the beam is subjected to central point load of 12 kN. So what is the maximum bending stress that we have to calculate here. This is given like this beam. This is the cross section and 150 depth and breadth is 60 mm, and it is subjected to a point load. Central point load is 12 kilonewton. So what we have to do, we have to calculate bending stress. Okay, so first we will see what is M. Bending stress, we know that formula, that is M by I is equal to sigma by y. So if you write in terms of sigma, then it becomes, you can write in any terms. Suppose if you write in terms of sigma, then what it is, M divided by I is equal to sigma divided by y. So sigma is equal to M into y divided by I. So for that we required M. So how we will get M? M is equal to, this is simply supported beam subjected to point load at the center. This I have explained while solving shear force and bending moment derivations. So M is equal to WL divided by 4. W is equal to 12 into 10 raised to 3 into L is 6 into 10 raised to 3 convert into millimeter divided by 4 is equal to 18 into 10 raised to 6 Newton millimeter. Okay. Now for this section modulus, you can use this formula, or M divided by I is equal to sigma divided by y. Any formula you can use. This is simple to remember. So I use this. Z is equal to BD square by 6 for rectangular section. So B is 60 into D is 150. So 150 square divided by 6 is equal to 225 into 10 raised to 3. Now maximum bending stress, that is given by sigma maximum is equal to M divided by Z, or y, how we can write M into I divided by Y maximum. That also you can write. In that case you have to calculate what is Y maximum. Y maximum is 150 divided by 2. Anything is fine. Okay. So now we will use this formula. Sigma is equal to M divided by Z. M is equal to 18 into 10 raised to 6 divided by 225 into 10 raised to 3. That is equal to 80 Newton per millimeter square or 80 MPa. Very simple example. Only you have to calculate what is M and what is Z. Or if you don't know Z also, no problem. You directly use that formula. M divided by I is equal to sigma divided by Y. So sigma is equal to M into Y divided by I. Anything is fine. Okay. Let us see one more example. A rectangular beam 300 mm deep is simply supported over a span of 4 meters. What uniformly distributed load the beam may carry if the bending stress is not to exceed 120 MPa? Take I is equal to 225 into 10 raised to 6 mm4. Here I is given and you have to calculate this load. Okay. W you have to calculate. This is uniformly distributed load. This is simply supported beam. It is subjected to UDL full, and this is given breadth and depth is given 300 mm deep, and span is equal to 4 meter. So we know first we have to calculate what is Y maximum, that is equal to D divided by 2. That is D is 300 divided by 2 is equal to 150 mm. Let W be the uniformly distributed load the beam can carry, that we have to calculate. Okay. Here we know Z is equal to I divided by Y maximum. Right. What is I? I is equal to 225 into 10 raised to 6 divided by 150. Okay. So you get Z is equal to 1.5 into 10 raised to 6 mm cube. Now moment of resistance. What is moment of resistance? That is equal to Z into sigma maximum. Because you know sigma maximum is equal to M divided by Z. So if you write in terms of M, M is equal to sigma maximum into Z. Sigma maximum, that is here it is given uniformly bending stress is given, that is 120 MPa. So substitute that 120 into Z. Z is equal to 1.5 into 10 raised to 6. Simplify this, you get this Answer. Now we know that a bending moment at the center of simply supported beam subjected to UDL, that is given by M is equal to WL square divided by 8. This I have explained while solving SFD and BMD. So if it is a simply supported beam subjected to UDL, M is equal to WL square by 8. We know M now, that is 180 into 10 raised to 6. Only one unknown, W into L square divided by 8. Simplify this, you get W is equal to 90 Newton per millimeter or 90 kilonewton per meter. Okay, like this you can calculate what is the load. Okay, I hope all of you understood. Thank you.